Okay, thank you. So, okay, yesterday, we have discussed the replica method. We have finished with the replica method, and the main result in this method is that you have a way to write the traces of integer powers of the density matrix. You have an identification of this object with the partition function in a very complicated manifold. Okay, it's a replicated manifold with conical singularities. Okay, so the idea is that once you have this, you can calculate the Renyi entropies, and the final step was to take this limit to obtain the entropy. Okay, so as we have discussed yesterday, both steps are quite difficult, and we don't have any systematic way to solve nor the first nor the second step. Okay, so in general, the partition function in such a complicated manifold is difficult to find. Okay, and also, even if you succeed with the first step, you can fail in the second. I mean, it's in general for a function which is defined only for integer values to find the analytic continuation. It can be very difficult. Of course, we are dealing with infinite dimensional density matrices. Okay, so there are examples where people can find Renyi entropies, but still they cannot find which is the entanglement entropy. Okay, so but for free fields, at least we can map this problem into a problem in a single plane manifold, okay, with a cut. But of course, we pay a price, and the price is that the fields now acquires a funny phase when crossing the cut, okay? So the relation, the equation is, let's take fermions am I writing? This is so when you approach the cut from above or from below, you have these phases. In the case of fermions, this case are just okay. And for scalars, this is the relation. Okay, so at the end, what you have now is, again, you need a partition function. This is just a notation, okay? Or perhaps you can say that you can call it in this way, and at the end you have to sum overall the case, okay? So in the case of a fermion, now you can think, okay, is this easier than this? Well, it's not clear to me if it's easier or not, but at least for fermions, we know how to do it. I mean, the idea is that these phases can be mimic, coupling the fermion to a gauge field, a pure gauge field, everywhere except in the boundary, I mean, in the singular points, okay, in the boundary of the region. In that way, it appears a current. This current can be bosonized, and what you get is that this partition function is nothing but correlators of vertex operators in a free scalar theory. You know the answer, you know how to sum overall case, and you get all the Renyi entropies, and also you can get the entropy, okay, the exact answer for the entropy. So let me give you some details of the calculation. It's quite easy, but the main idea is what I have told you. So what you have to do is to introduce a pure gauge, okay? Pure gauge everywhere except in the singularities. Or let's say this has K, this is, now I will tell you which is A. A is one of the boundaries. We are saying we are in one dimension, okay? We have N, no, let's say P intervals, just not to be confused with N precon. And we are going to say, okay, so this is A1, B1, A2, and go on, okay? So this is we have this, and you can write a mu, and let's say K. We have a K somewhere. This is 2 pi over N. Then you have to sum over the intervals. Okay, this is go up to, and you have, so only in the boundary, okay? So with this, okay, this is the idea, okay? This is the kind of gauge field we are introducing. So the partition function is just given by this A mu K coupled to the Dirac current. Let's write it like this, okay? So this is the main idea. Now you can write this in terms of a scalar field, a boson, and so if you write this as, well, I'm not sure about this pi, but I believe it's mu, this is mu, like this. What you get, and you can check that this is nothing but, it has this, I believe it's a square of 4 pi. You have a K over N. You have a sum till P. And what you have here is BE, okay? This is like this. This is I. Like this, okay? And these are vertex operators, okay? That you know the answer. So I will write the answer. So this is, again, an exercise you can do. You can check that the solution is the Renyi entropies are 1/6 n plus 1 over n of a function, and this function is, again, j, and you have log I minus bi, then you have a sum. I mean, you have all the combinations, okay? This is of distances. Then you have the same for the b's. And then this is a cutoff that take care of the coincidences points, okay, the split coincidence points, okay. So this is the expression of f, okay, and okay, it's clear here that. Well, of course, from here you have that S is just, okay, it's just 1/3 this function, and for one interval, the answer is just 1/3 log A. Let's call it L over epsilon, which is what you know from the very beginning, okay? What is interesting here is that for one interval, you can say that for any conformal field theory, this is the answer, putting a C here, okay, the Virasoro central charge. So you can generalize this result for any conformal field theory. But this is not true in general for P intervals. This was the first attempt to give an answer for the n intervals for any conformal field theory. The first answer was to put here a C, and this is not true. Only for the fermion. Okay, the fermion has special properties. It's quite. I really don't know why it's so special, but for example. What is interesting is that it has an extensive mutual information, for example, which is not true in general, okay? Let me see if I can show you some pictures. No, I believe I don't have I don't have pictures of that. But so let's some comments. So the one interval result can be generalized to any conformal field theory. Second, if you have many intervals, this is not true. Third, which is interesting, is that the fermions are quite special in a sense. And what is true only for fermions is that, for example, the mutual information is extensive in this sense. Okay.
It is not true for free bosons?
No.
But in 2 dimensions, free fermions and free bosons are really the same.
The point is that it's not true for scalars, for non-compactified scalars. And when you take the rate, for a compactified scalar probably is true, but not for a non-compactified scalar. Yeah, it's quite surprising this. This is only true for fermions. Yeah, yes? Yeah, this is an old question. I mean, as you can describe, I mean, there's a duality between the Ising model. I mean, you can describe the Ising model with a fermion, and for many years we have different results for a fermion calculated in this way, and for the Ising model, for example. And we didn't understand why, if it's exactly the same theory. So for many years, we were thinking, okay, it's perhaps it's something related to, I mean, the field content. It seems to be the same, but there's something special.
It's not quite the same, right? Because
it's not quite exactly. Yes, it's not quite the same,
So
and it's very interesting that the entropy knows about that. You can distinguish the two. Yes, it's.
The resolution is believed to be related to the fact that it's not just a naive free fermion.
Yes, yes, yes. There's a paper by Hedrick, very nice paper, where he found a solution for that. So I believe that this is all I want to discuss about explicit calculations. And I would like to discuss, I mean, to dedicate the last part of the lecture in a different thing, because up to here it seems clear that the tools we have to calculate things in this for the entanglement entropy are clearly no so robust as in the standard quantum field theory field, okay? But still, what I want to show you is that there are applications of the entanglement entropy, for example, related to the C theorem, which are very difficult to find in the side of the quantum field theory, and it seems very easy to find in the entanglement entropy scenario, okay? So perhaps to erase a little bit the impression that there are not too many things to calculate with the available methods we have so far, still there are many relevant results you can get using entanglement entropy, which give you with a deep meaning in the structure of quantum field theory, such as the C theorems, okay? So I'm not going to talk much about C theorems because Zohar has done it yet. But just let me give you some comments. This, sorry?
Can I have one question?
Yes. Who is talking? Ah, you. Okay, sorry. I'm not hearing it, but I'm not seeing, watching. Yes.
The difference between the fermion and the boson calculations you just mentioned, has it got to do with the fact that this Mandal-Storm relationship is non-local? Tracking the fermion in terms of the boson involves the string? Is that related in some way?
Yes.
This is the question that Gautam was raising for the Eisenhower, for example.
Yes, yes, it's the same question. I believe. The point is that for compactify scalars, we don't know how to do the calculation. For example, I cannot check what happens with a compactify scalar because I don't know how to do the calculation. I don't know how to put it in the lattice, for example. So I don't know the answer. But with the Ising model, there are people that have work and have some results and are completely different from this. It seems that in the Ising model, this function I show you, I mean, you cannot, the answer is not given by C/3 times the function. It has a correction, okay? And from here, you don't see it. Yeah. So the C theorems, okay, this is an idea that appeared in '86. It was Samologikov who formulated the C theorem in 1+1 dimensions. And this is something that gives you a constraint on the renormalization group flow, okay? The renormalization group flow tells you about changes in the theory with the scale, interpolates between the ultraviolet to the infrared. Of course, in the fixed point, the theory looks the same at all scales. And what the theorem says is that exists a universal function, dimensionless, decreasing along the renormalization group trajectories. And this function takes universal values at the fixed point, which are proportional to the Virasoro central charge. Basically, this is the statement of the theorem. It's clear that this gives you a kind of ordering of theories in the space of theories, okay? And the people understand this irreversibility as due to the loss of degrees of freedom. This is the interpretation, the most popular interpretation. In Samologikov theorem, this interpolating function is given in terms of two-point correlators of the stress tensor, okay, as Zohar has shown you. And what I want to show you now is that the same thing can be proved using the entanglement entropy. So let's call it entropic C theorem, okay? The ingredients we are going to use are strong subadditivity, And we are going to use, this is something, a property for for entanglement entropy, but for geometric entropy, in the sense that suppose you have a region, this is a Cauchy surface, okay? We have this is the boundary, and this is the causal domain, okay, of your region. What we know is that the entropy, suppose that we take two different Cauchy surfaces, the entropy is the same. I mean, people used to say, like to say that the entropy is a function of the diamond, okay, or if you want, is a function of the boundary, okay. So we are going to use these two things. This is due to unitarity, okay. So we need unitarity for this, and in 1 + 1 dimensions, we only have intervals, okay? So we are going to use intervals, and if we want to use strong subadditivity, we need at least 2, okay? But this is time. These are the null lines, okay? This is called the causal domain, okay, of the. So to get relevant information from the strong subadditivity, let me remind you. Well, we are going to use different letters, but still, it's the same. I mean, as the entanglement entropy is a divergent quantity, if you want to extract some information from this inequality, you need to cancel the singularities. Otherwise, it's trivial, okay, the information you have from there. So the first idea is that you need that the regions, the union and the intersections, you need the same kind of singularities in all these regions, okay? And you need the same number of regions in the right-hand side and the left-hand side in order to cancel, okay? So
in the first lecture, you said that there is no rigorous proof of the statement in quantum field theory. But was that because of the infinities and because of the special regions that you considered?
No. This is true. I mean, strong subadditivity, it's true for regions. There's no problem with regions. What I was saying is that when you think in union and intersection of algebras, this is different, okay? If instead of thinking on regions, you are thinking on algebras, I mean, at least the proof as it is now, it's not clear that it holds. I mean, you need, for this to be valid, you need a tensor product of Hilbert spaces. This is the way that it was proven. Okay, so which is the idea? You need two intervals, okay? Yes? Yeah. No, I mean, this is very simple. The only thing you are saying is that if your theory is unitary, then it cannot happen that if you change your Cauchy surface, keeping the boundary fixed, the entropy cannot notice that something had happened, Okay, this is the only thing we are saying with this. Okay. For manifolds, I don't know. I don't know. If the manifold is not compact. I'm not sure.
No, I think we just want, I would have said that all you care about is that all the domains are very defined. And then each of the Cauchy slices have very defined domain constraints.
I'm not sure about that. Are you sure? Yes? Okay. He's not pretty sure, but still. Okay. So what is the construction we need? Let's take two intervals. But the planar construction is not useful. And this is an exercise also. Suppose you take this and this. This is A, B, C, and D. You apply a strong subadditivity here, and you try to get some information about the entropy. You will see that this is not strong enough. What you need instead, my drawings are horrible, but well, this is, I don't know. Okay. Let's say this, 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 and this. This is interval A. This is B. And I don't know why I use this. This is A1, no, 2 equal to B2. And this is taking this, has this size, and I call this part, it's impossible to understand, right? Yes. No, wait. No, I will try to do it better. Wait. Perhaps. Or someone can do it for me, but wait. No. It's not the color of the chalk. It's my drawing. Okay. No, it's impossible. But so this is A. No, this is A. This is B. Okay, we are taking two intervals relatively boosted to each other. Okay. So this is V. It's going to take a long time. A. Again, this is R. This is A2 equal B2. This part is A1, and you will see why I'm putting so many letters, and this is this. So using this, it's clear that, well, of course, this is the intersection, and this is the union, okay? We are going to use a strong subadditivity. And from here, we know that we can write that the entropy of A, that's why I'm putting so many letters, is the same as the entropy if you take this. Instead of A, you take this and this, okay? Is it clear? And the entropy of B is the same as, this is B, so is this union, okay? So we are using this, and now we are going to use strong subadditivity. And what you get is S A1 A2 plus S B1 B2 greater than S A2 plus S A1 A2 B1. Okay? Do you agree? And now if this is big R and this is a small r, what you have is that we are choosing A equal to B equal to square root. Okay? So what you get is that twice has to be bigger than S R S big R. Okay? And now if you take this, the infinite, I mean, epsilon going to 0, you can write an infinitesimal relation between the second derivative of S and the first derivative, which is, sorry, this is R. Is it right or not? Let me see. Yes. Plus, let's write it all in the same, like this, and this is what you obtain. Okay? And from here, you can read that it's possible to write a function, a dimensionless function, in terms of the entropy, which is, from here, you can see that you can write this in such a way that the derivative of this function and here we have a C theorem, okay? This function, again, at the fixed point, is proportional to the Virasoro central charge. Because as I show you with the fermion example, the result is, at the conformal point, is this. Okay. So let me show you how it looks. Okay. So this is the first two. I mean, from top to bottom, we have the first two are the Samolosnikov C functions for a scalar and fermion, okay, and a Dirac field. And these two are the entropic C functions. But what is interesting is that in the Samolosnikov case, the scalar is bigger than the fermion. And in the entropic case, the fermion C function is always bigger than the scalar C function.
This slope is also sharply going to 0, is that right for all of them?
Well, for the scalar, you have here some problems. Yes, it's very deep in there. But this, I mean, in principle, you can think, okay, but perhaps, I mean, these functions encoded the same information or not. It's not clear from the expressions how to relate one to each other, okay? But what I have found is at least a way to say that there's no relation between the entropic C functions and the samologic of C function. And the argument goes like this. You know that any correlation function can admit an spectral decomposition, okay? You have a spectral density, okay? You can write it as an integral over masses of the free correlator with a weight given by this spectral density. And let me see. Okay, there's a relation. This is Capelli, Friedman, and Latorre found that with this spectral density, you can build a whole family of central samological C functions. So it's not unique at all. So you can ask if the entropic C function belongs to this huge family of central functions. And the answer is no. And the way you can see it is that, okay, the result by Capelli, Friedman, and Latorre is very old, in 91. They show that you can find, by convolutions with the spectral density, you can, well, let's say, this is a mass, this is the spectral density you get from the correlators. Of course, the correlators you have to consider here are correlators of the stress tensor, okay, which are the ones that use Samologikov to prove the theorem. And you can put here a function that has to be, I believe that is 1 in 0. It has to be 0 in infinity, and it has to be decreasing. I believe that this is the only conditions you have to ask to this general function in order to obtain a new C function, okay? This function is as good as the one defined by Samologikov, okay? It's decreasing, it's dimensionless, is one of a huge family, this one. So if you ask if the entropic C function I have shown you belongs to this kind of families, we can prove that the answer is no. And just looking at, I mean, you can try to do the explicit calculation, but there's a simpler way to do it. We know this spectral density for scalars and for fermions. And from the relation, there's explicit relation between these spectral densities, which tells you that if your function belongs to this family, between the scalar and a Dirac field, you need horrible. Wait. Okay. They satisfy this equation. So this is always bigger than this. And on our C function, it's exactly on the other way, okay?
Marina,
Yes.
I'm a bit confused about how to interpret your inequality. So you found that there's this function CR is equal to RS prime, such that C prime of R is monotonic.
Yes, and
Now,
at the
if
fixed
there is-
point, it takes.
So how does it become a monotonicity with respect to the UV cutoff? I mean, are you saying that C of R, if I understand that if C of R has a log term, then that log has to come with R and the UV cutoff. Therefore, the derivative with respect to R is the same as the derivative with respect to the cutoff.
Yeah.
However, we are talking about massive theories here, because in between fixed points, we are at massive theories.
Mm-hmm.
So there's another mass scale. So how do I relate the R derivative to the cutoff derivative, right? Because there is another mass scale in the theory. Because I'm flowing from a UV to R.
Yes, but you can show that this is. I mean, this gives you. If you want a renormalization group equation, you can show it. Is exactly, I mean, with this is enough to give an interpretation in terms of a renormalization group equation. Even if, I mean, of course, here you will have M, this will depend on M and R, you are right.
I'm thinking Kalan-Simmons
Yes,
equation.
yes,
So
you
the-
can write a Kalan-Simansic equation for this.
But the momentum derivatives become the same thing as the cutoff derivatives.
Yes,
If there are no beta functions in the Kalan-Simmons equation.
yes,
If there are, then I can't say that the momentum derivative is the same as the cutoff derivative, right? I mean, this R derivative is like a momentum derivative,
yes.
right? So, but away from fixed points, then these two things will differ by the appearance of the beta function terms in the Kalan-Simmons equation.
No. You can rearrange things in order to write a Kalan-Simansic equation. It's exactly the same thing. Yes. Don't worry about this. Yes, this is. So, do I have still time to discuss the three-dimensional case or not?
Yeah.
Yes. Okay. I have half an hour or not? No. Half an hour, no.
25 minutes?
Okay. Okay. So now, once you get this, you say, okay, people have worked a lot trying to generalize this idea for higher dimensions. And only recently, Zohar has proved for 4 dimensions a C theorem. But you see, almost, I don't know, 20 years later, okay, it has taken a lot of time. But for odd dimensions, we don't have any result, okay? But still we have, as Zohar told us, we have some candidates for a C theorem in 2+1. We have the proposal by Klebanov and collaborators talking about the free energy, okay, the constant term in the free energy for spheres. We have the holographic C theorems talking again about the constant term of the entanglement entropy for circles. We have the proposal by Liu and Mesey talking again about spheres and the constant term of the entanglement entropy for spheres. So our problem, when we solve this problem, we try to think in an easy generalization, but the point is that, again, as I told you, you need regions such that the intersection and the union has the same shape. And in 1 + 1 was very easy because you have intervals. But when you go to 2 + 1, and everybody was saying that it has to be circles, we're saying, okay, we cannot do it with circles because the union and the intersection is not a circle. So it was clear that take 2 circles, it was not going to be enough to extract information about from the strong subadditivity. So look at this. This is a planar construction. It's not going to be enough either. But just this is easier to see. I mean, at the end, you are going to I mean, you will need to boost the circles, but it's easier to see it in this planar construction. The idea is that if you take not 2, but many circles, okay, and you rotate the circles an angle, this is the angle 2 pi k over n, and you take n going to infinity, what you get is this. And as you see, the regions which appear in this part looks like circles. Okay, as n grows, you obtain more and more something that looks like a circle. Okay, and this is we're saying, okay, so with an infinite number of circles, we can try to use a strong subadditivity. We have the same number. Here we have an example with 3, okay, and here it's written for any number of regions. What you can check is that you have the same number of regions on both sides of the inequality. This is good. You have the same shapes, so this is good to cancel inequalities. But the problem is that this wiggle circle, it has angles. And even if you go to n, if you turn n to infinity, these angles don't disappear. And as I show you in the first talk, the angles gives you logarithmic divergences. And so you will have, in this part, logarithmic divergences, and in this part, no. So it's not good, this planar construction. But when you approach the light cone, the angles, okay, go to pi, and we know that the coefficient for pi is 0 in the log divergent part. And also the perimeter approach the perimeter of a circle of this radius. So this is the right way to do it. Okay. So it's very similar to this. It's the same thing, but now what you are doing is taking circles, you rotate the circles, okay, but they have to be seated on the light cone in order to get rid of the angles, okay? The logarithmic divergence is coming from the angles. Okay, I'm not going to show you the details of the calculation. It is not difficult, but what you get at the end is exactly the same philosophy I use here, is this condition for the entropy. And from here, again, you can write an interpolation function, which depends now we have in 1 plus 1, we have this piece only. Here, we have this. It depends on the entanglement entropy. And we know that at fixed points, the entropy has this linear form. And when you check this, the value at the fixed point, you get the constant term in the entanglement entropy. And okay, so you have proved that this function is decreasing when going from the UV to the infrared, but I was talking yesterday or the day before about the ambiguities we have in this constant term. There's, okay, and to have a C theorem is not enough to have a decreasing function from the UV to the infrared. Okay, you need also to have a good definition at the fixed points. Okay, a universal definition at the fixed points. And with the entropy, it's not clear that this term is well defined, since you have ambiguities in the definition of what is the size, okay? And as I showed you the first 2 days ago, you can, in the lattice, for example, you can change your regularization, the way you measure R in terms of lattice spaces, and you change immediately the value of the constant term. Of course, you can say, okay, but I don't care. I have, on one hand, I have the proof for the decreasing using entanglement entropy, and I'm going to use a different argument coming from the free energy in terms of counterterms, as Sohar told us. And that's it. I take one part from here, one part from here, and I have a C theorem. But it would be nicer if you have all the arguments in the same framework, okay? But, so the idea is to get rid of these ambiguities. You can use mutual information. And again, we are going to use this way of regularized the entropy using the mutual information. In such a way that all the coefficients in the expansion are universal, okay? And but you would ask, okay, if by definition if you have this construction, you would say, okay, if I use mutual information, you have this is the entropy of the small, the smaller circle here. You have the entropy of the big circle, okay? But still you have the entropy of this circular annular strip, okay? And you can check that in the limit that this goes to 0, the entropy of this is, I mean, at least you have no contributions to the constant term. This is what we have proved in a paper. It's going to appear, I don't know, in these days. Moreover, you can start using mutual information, and you can forget about entanglement entropy, the proof I have shown you, and you can say exactly, you can prove the decreasing using directly the mutual information. So you have everything written in terms of the same thing, okay? So, okay, this is all. Do you have questions or question?
So where are the positive domains in the higher dimensional picture as we had?
In the
The causal domains. I don't. So where do the causal domains appear here?
the causal domain, what is the problem with that? I mean, I'm using two things. I'm thinking in relativistic theories, Lorentz invariance. So I'm asking for Lorentz invariance, and I'm asking unitarity. This is the only things I'm asking.
No, I think he's asking where are these causal diamonds in the three-dimensional picture. I mean, there was a picture that you had shown in one of the slides before.
Not this one. This one. Here. This is the same. It's exactly the same construction than in 1 + 1. Exactly the same.
Is there any hope of doing this in 4 dimensions?
In 4 dimensions, you need more than a strong subadditivity. I mean, in 4 dimensions, it's easy to think in the sets, because you have intersections and unions. It's easy again, as in 1 + 1. But the problem is that with this kind of inequalities, the most you can get is second derivatives. And with second derivatives, you cannot kill the divergences. So you need something else. Yes. But of course, we are working on that. Yes.
For C theorem, it has to be monotonically decreasing. It cannot be less than equal to, it has to be less than. Derivative has to be less than 0, cannot be less than equal to 0. Because it has to be monotonically decreasing.
Yes.
Derivative has to be just less than.
No. The inequality is saturated at the fixed points.
Say it again, please. Because the answer was so sure no. So let me see. What have you said?
I thought that it should be less than 0, it cannot be less than equal to 0. I just thought that it has to be monotonically decreasing. That's why the derivative has to be just less than 0.
Here.
No, that derivative, the C naught dash has to be less than equal to 0.
Here. That's right. It's
I thought it has to be just less than 0 because.
you were complaining about the equal. Yeah. Okay. Now I understand the no. Yes. Yes, okay.
Any other questions? Yes, please.
General question. Can we talk about entanglement? I mean, not of spatial regions, but that in momentum space. Can we talk about entanglements of regions in momentum space?
In momentum space. The problem is that once I mean, you need this independence on the Cauchy surface. So I don't know in momentum space how to.
No, not in this context. Not in this particular.
Okay. The point is that the properties are quite different when you trace over degrees of freedom which are not spatial degrees of freedom. For example, you will not get any more this area law, for example. The entropy, it's not going to have a leading term going as an area term. You are going to have something going as the volume, for example. But still, there are people working on that. Or for example, you can think on a fermion with two chiralities, and you trace over one of the chiralities, and to see what happens. is this related to the entanglement entropy, yes or no? Or for example, in spin chains, you have 2 spin chains and you trace over one of them and you can see what happens. Yeah, there are things done in this direction.
Okay, if there are no further questions, let's thank Marina for a wonderful set of lectures.